Okay, so we'll continue with a few more word problems involving fractions. The first problem reads, a truck contains 2/3 of a ton of dirt, but is only 3/10 full. How many tons of dirt can the truck hold? Again, as we mentioned with pretty much every word problem, our hope is that students are proficient enough in arithmetic to simply read this problem and recognize the correct arithmetic directly from the words of the problem. And if we really understand partitive division, we can actually do that with this problem, because we can see that this problem reads, the truck contains 2/3 of a ton, but is only 3/10 full. So really this is saying 2/3 is 3/10 of what, which from a partitive division interpretation corresponds to the arithmetic 2/3 divided by 3/10. Now that's pretty difficult to see unless we're really, really solid with partitive division. So another way of solving this problem is to use a bar diagram. The bar diagram usually can serve as the bridge between the words in a problem and the arithmetic necessary to solve the problem. So if we start by drawing a diagram, whenever my students have trouble with these problems, I tell them to start by drawing a bar. Everyone can draw a bar, and oftentimes if you simply just draw a bar, then you can work your way through the rest of the problem. So this bar represents the entire truck. And it can be confusing at the outset, since there are two fractions in this problem, how are we going to divide up this bar? But if we think about it, the truck contains 2/3 of a ton of dirt, but is 3/10 full. So if the entire bar represents the truck is 3/10 full, so we want to represent the fraction 3/10. We do so by splitting the bar into 10 pieces and shading 3 of them. 4, 5, 6, 7, 8, 9, 10. Got to make sure I've got 10. Okay, so this fraction this picture represents the fraction 3/10 of the truck, and we are told that 2/3 of a ton of dirt is equivalent to 3/10 of the entire truck. So I can label these 3 pieces with the fraction 2/3, or 2/3 of a ton if you like. The question is now asking, how much dirt could the entire truck hold? Well, the entire bar represents the entire truck, so our question mark is going to bracket the entire bar. Okay, so this is a diagram that models this situation. Now it's a little bit clearer that the question is asking 2/3 is 3/10 of what, which would lead us to the correct arithmetic. But let's finish the problem by writing a unit sentence and solving it with arithmetic. Our unit sentence is going to be, in this case, 1, 2, 3 units is equivalent to 2/3. Or 2/3 of a ton if you like. From partitive division, we know that if 3 units is the same as 2/3, then 1 unit is certainly the same as 2/3 divided by 3. From fraction arithmetic, namely fraction division, we understand that 2/3 divided by 3 is the same as 2/3 times 1/3, which in this case is 2/9. So 1 unit represents 2/9, or 2/9 of a ton of dirt. The question is asking how much dirt does the entire truck hold. There are 10 units that comprise the entire truck, so we are interested in 10 units. Again, our models of multiplication tell us if we know what 1 unit is equal to, then to figure out what 10 units are equal to, we simply multiply by 10. So if 1 unit is 2/9, 10 units is 2/9 times 10, which is 20/9. And that is our answer. Our truck holds 20/9, or in this case 2 2/9 tons of dirt. Okay, now the next problem we're going to look at is also taken from a 5th grade Singapore book, and it's a little bit different than the problems we've looked at so far, in that it involves remainders. So it's a 2-step problem involving remainders. David had 1,280 eggs. He sold 3/5 of them on Saturday and 1/4 of the remainder on Sunday. Not 1/4 of the total, 1/4 of the remainder. The question is asking for the total number of eggs he sold. Okay? So again, let's just proceed. Again, we're not going to be able to pick off the arithmetic straight away because this is a 2-step problem. Okay? So bar diagrams are going to be far more useful in these types of problems because they're multi-step. So we start, as we always do, simply by drawing a bar. The original bar that we draw is going to represent the whole. In this case, the whole is the total number of eggs that David had. In this case, he had 1,280 eggs. And now we just go statement by statement. The first statement is he sold 3/5 of them on Saturday. So we can easily record 3/5 of this entire bar by chopping the bar into 5 pieces and shading 3. Now, the question goes on and says he sold 1/4 of the remaining eggs on Sunday. Now, if the shaded part of the bar represents the eggs he already sold, the unshaded part is going to represent the remainder. So we actually have to represent not 1/4 of the entire bar, but just 1/4 of the unshaded part, because the unshaded part again represents the remainder. Now the numbers set up pretty nicely in this problem. There are 2 unshaded pieces. We have to represent 1/4 of that. We could do that by cutting each of these remaining pieces into 2 pieces and then taking one of those 4 pieces that remains. Now, as we've seen with our previous unit sentences, if we're going to come up with a unit sentence at the end, every part of the diagram needs to be exactly the same size. So if I want to chop the remaining 2 pieces in half, as I definitely want to do, because now it's going to be very easy to represent 1/4 of the remainder, I need to chop all of the original pieces in half. Because again, I need a unit sentence at the end of this, and the unit sentence is going to come from the fact that all of the pieces in the diagram are the same size. Notice again what has happened is that I've renamed my original fraction 3/5 of the eggs as 6/10. So now I still have recorded that 3/5 of the eggs were sold on Saturday. I just renamed that as 6/10. Now to represent 1/4 of the remainder being sold on Sunday, I can just shade again, maybe differently. And this shaded piece represents the 1/4 of the remainder that were sold on Sunday. The question asks the total number of eggs sold. That's going to be the total shaded area of the bars. The first shading represents what's sold on Saturday. The second shading represents what's sold on Sunday. The total shading represents the total number of eggs that were sold. And now I can easily come up with a unit sentence, right? The next part of my process is a unit sentence. I started with 5 pieces of my diagram, but I ended up cutting each of those pieces in half. So I now have 10 total pieces of the diagram. So my unit sentence is going to be 10 units is equal to 1,280. And if we look at the diagram, I'm actually interested in 7 units. So to get from 10 units down to 7 units, I first use partitive division to figure out what 1 unit is equal to. We know again if 10 units is 1,280, then 1 unit is certainly 1,280 divided by 10, which is 128. And now I look at my diagram and I'm interested in 7 units. So models of multiplication tell me that if 1 unit is 128, then 7 units is the same as 128 multiplied by 7. Now again, as a teacher, you can set up problems based on the types of computations you want your students to do. If you want your students to solve problems to practice mental math, then you can set up the numbers in the problem so that the computations will be mental math computations. On the other hand, you may want your students to practice the algorithms, so you can set up the numbers in your problem so your students can solve the problem with an algorithm. In this case, maybe this doesn't really seem like a mental math problem. Maybe we just use the algorithm on this. We could maybe think of this as mental math as 100 times 7 and then 28 times 7. And if we did that, using the distributive property from a mental math technique we discussed earlier, 100 times 7 is, of course, 700. 28 times 7 is, we can think of as 30 times 7 minus 2 times 7. 30 times 7 is 210. 2 times 7 is 14. 210 minus 14 is 196. 4896. And again, I'm always out of room to write my complete sentences, but our complete sentence answer would be David sold 896 eggs over the weekend. Okay, so in this type of problem involving remainders, we can actually represent the remainder on the original diagram because the numbers turned out really nice. It turned out that there were 2 original units left over, and I only needed to make 4 units total out of those 2 units. So it was easy to do by just splitting each of the original units in half. In the next problem, which is also taken from a 5th grade Singapore book, the numbers don't line up as nicely, so we have an alternate technique for for handling these problems with remainders. So this problem is very similar to the previous problem. Mr. Ricci spent 1/3 of his salary on food, and again, and 2/5, and there's a typo here, it should be 2/5 of the remainder. My apologies. So he spent 1/3 of his salary on food and 2/5 of the remainder on transport. If he had $600 left over, what is his salary? So again, we start the problem simply by drawing a bar. The bar that we draw at the outset represents the whole. In this case, the whole is his salary. And actually, that's what the question is asking. So the question in this case is going to, or the question mark in this case is going to bracket the entire bar. And now we can just go step by step through the problem. He spent 1/3 of his salary on food. So we can illustrate 1/3 of his salary by simply modeling 1/3 of the whole. Cut the whole into 3 pieces and shade 1. Now, in this, it goes on to say he spent 2/5 of the remainder on transport. Okay? Now, in this problem, like the last problem, the remainder is the stuff that we haven't shaded yet. This is what he spent already, and the unshaded portion is the remainder. Now, one technique would be to split each of these pieces into 5 additional pieces, because again, remember, we have to somehow model 2/5 of the remainder. Okay? That might lead us to a pretty messy diagram because we're going to have a lot of units piling up. So an alternate technique is to just draw a new bar, a fresh bar to represent the remainder. So what we might do is draw just a little arrow that takes us down to a new diagram. And we want to be really careful that our new bar is the same length as the remaining part of our original bar. So now we have a fresh bar to deal with the remainder, so we can easily talk about 2/5 of the remainder. This bar here represents the remainder, so to talk about 2/5 of it, we can simply split it into 5 pieces and shade 2 of them. So this bar here represents the shaded part of this bar here represents 2/5 of the remainder. The last part of the problem says he had $600 left over. Okay, so since this bar down here represents the original remainder, and since he spent the shaded portion of this remainder, the amount of money he has left over is the unshaded part of the second bar. So that's what the 600 represents. So this is another way of handling problems with remainders. In fact, we could have done something similar on the last problem involving remainders. Now, the solution process is going to be slightly different than it has been previously, simply because we don't have a uniform unit in this problem. We have 2 different bars, and the units in each bar are different. To distinguish between them, I'm just going to call these units small units, and these units large units, because these are small and these are large. The unit sentence that we can come up with from this picture, or from this entire diagram, comes from the second bar, comes from the remainder bar. So really, all we can say is that 3 of these small units are equivalent to 600. From partitive division, of course, if 3 small units is 600, then 1 small unit is equivalent to 600 divided by 3, which is 200. And what we need actually is to figure out what this entire remainder bar is. Because we can, again, eventually, we need to figure out what 3 large units are equal to. So eventually, we're going to have to make a transition from small units to large units. The only way we can do that is if we figure out what 5 small units are. Because 5 small units are equivalent to 2 large units. So if 1 small unit is 200, 5 small units, again, from our models of multiplication, 5 times 200, or 1,000. But as we see from our diagram, 5 small units is exactly the same as 2 large units. So 2 large units is 1,000 as well. Now we're working with the units that we need. We can see that 1 large unit is 500, 1,000 divided by 2. Our question mark is bracketing 3 large units, so we have to figure out what 3 large units is equal to. 3 large units equals 1,500. And again, I'm out of room for a complete sentence, but that is Mr. Ricci's salary in this problem. So the last two problems illustrate two different ways of handling fraction arithmetic problems, or fraction word problems, I should say, that involve remainders. On the one hand, we can just use the exact same bar by chopping and then chopping again. On the other hand, we can use two bars, an original bar and then a new bar that represents the remainder. The last problem we're going to look at is another problem taken from a 5th grade Singapore book that is a fraction multiplication problem. This problem reads, there are 1,500 workers in a factory, 5/6 of them are men, 3/10 of the men are single. How many single male workers are there in the factory? Okay. Again, we hope that our students are going to just, from the wording of the problem, recognize the correct arithmetic needed to solve the problem. This is kind of a two-step problem in that first we need to figure out the number of men before we can figure out the number of single men. If we can't see the correct arithmetic just from the words of the problem, it is our hope that a diagram will form the bridge from the words to the correct arithmetic. Again, our first step is always just to draw a bar. And the bar represents the whole, and in this case the whole is the 1,500 workers that are at the factory. So we label the entire bar 1,500. Now, 5/6 of them are men. Again, we just go step by step in creating our diagram. 5/6 of them are men. We know how to represent the fraction 5/6. We just chop the bar into 6 pieces and shade 5 of them. Now, 3/10 of the men are single, okay? So the men are represented by the shaded part of the diagram. And we somehow need to record 3/10 of the shaded part of the diagram. Again, in this problem, the numbers set up quite nicely. There are 5 shaded pieces. We somehow need to represent 3/10 of the shaded part. So if we cut each piece in half, we're now going to go from 5 shaded pieces to 10 shaded pieces. And if we have 10 total pieces, it's very easy to represent the fraction 3/10. So we're going to cut each of these original pieces in half. Each of them, not just the shaded ones. If we only cut the shaded ones in half, we're not going to be able to come up with a unit sentence because not all of the pieces in the diagram will be the same size. So we actually want to cut all of the pieces in half so that now, again, all of the pieces in the diagram are the same size. We need that to be able to create a unit sentence. So now, again, in effect, what I've done is I've renamed my original fraction 5/6 10/12. I didn't change the shading at all, but now 10 pieces are shaded. There are 12 pieces total. So the fraction of men has been renamed 10/12 from 5/6. If I need to represent 3/10 of the shaded part, I can do that easily now. There are 10 shaded pieces. To represent 3/10 of the shaded pieces, I just need to shade again 3 pieces. And the doubly shaded part of the diagram is what I want. The original shading represents the men. The doubly shaded part represents the men that are single. And the question is asking how many single men are at the factory. So the question mark is going to bracket the 3 pieces that have been shaded twice. Okay? So oftentimes we'll do this with word problems that involve fractions. We will chop the original diagram into a certain number of pieces based on a fraction that's given in the problem. And then we'll need to divide those pieces again. That's what we did here. Now, again, the reason why we wanted to shade or chop all of the original pieces in half is so we can obtain a unit sentence. All of these pieces are exactly the same size, so that means they're all units. And it turns out that there are 12 of them total. 12 units is equivalent to 1,500. That is our unit sentence. Again, this is partitive division. If 12 units is 1,500, then 1 unit is 1,500 divided by 12. As we talked about with a couple of examples ago, as a teacher, you can set up the numbers in the problem to reflect the types of computations you want your students to practice. If you want them practicing the algorithm, you can set up the numbers in the problem so that they would have to solve the problem with an algorithm. A problem like this, however, you may be able to use mental math. We may be able to split the 1,500 up into, for example, 1,200 plus 300, and then divide by 12. So this problem now becomes 1,200 divided by 12 plus 300 divided by 12. Well, 1,200 divided by 12 is quite obviously 100. 300 divided by 12 is 25. So we get 125 for an answer to what 1 unit is equivalent to. 1 unit is 125. If we look at our diagram, we're interested in 3 units. Again, our models of multiplication tell us that if 1 unit is 125, 3 units is 125 times 3, which is 375. Once again, I'm out of room, but we would write a complete sentence answer. 375 male workers work at the factory, or single male workers work at the factory.